What is up, YouTube? Welcome back to another episode on Code with Annie. And in this particular episode, we're going to take a look at the Java code implementation for selection sort algorithm. In the last video, we saw what was selection sort and how it does the sorting. There was a detailed explanation, and this is just for your quick recap on what was happening. We initially had two positions initially pointing to the same element, which is the starting element 130. We assume that this is the minimum element. And then we start comparing 130 against all the elements in the array, and as soon as we find something less than 130, we used to replace the value of min with that particular element. For instance, here 20 was replaced initially, and then again 1 gets replaced, and then after that we observe that 1 is the least element in this entire array, and therefore by the end of the first iteration we see that min value is 1 and the position of 1 is nothing but 2 0 1 2, and therefore we swap the original position of the element we started off with, which is 130, with the position of the main element, which is 2. So 1 and 130 get swapped. So after the first iteration in selection sort, the least element in the array comes to the first position. Likewise, this happens for all subsequent elements, and one by one the appropriate elements are placed in their respective positions, and when we reach the end of the array, we have the array completely sorted in the ascending order if this is going to be an ascending sort. Now, if you want to implement this logic with everything that you see here as a pseudocode in Java, this is how it will look like. So what I'm trying to do here is I have an array of elements 25, 100, 10 and 1, and I'm running selection sort on this array, and I start with the position 0, which is 12 20. So what I do is I pass the array and the position I start with, which is 0, obviously. And what I'm doing here is I'm checking if this position is equal to the last element, which means I have reached till the end. If I reach till the end, I know that the array is sorted, therefore I just return the array. If not, this array.length -1, because the length of the array is 5 and the last element's position is going to be 4, because as you recall, array starts at 0. So if I reach the last element, there is nothing more to compare with on the right side of the array, therefore I just return the array. This is my exit condition. After that, what I do is, if this is not the case, I assign min as the array of position. In this case, when I start off with 20, min will be 20, swap position will be equal to position. So position is 0, swap position is also 0 initially. And then I start looking at all the elements from position plus 1, which is from 1 all the way to 4. 1, 2, 3, 4. So as and when I see, I compare the element at the position I and with the element that I have assigned as min, which is 20. So I compare 5 with 20, 100 with 20, 10 with 20, and 1 with 20. So when I see 5 with 20, 5 is less than 20, therefore min becomes 5, and the swap position will also point to the position of 5. Then 100 is not less than 5, 10 is not less than 5, 1 is less than 5. So now the new min becomes value 1, and the swap position is updated to the position of 1, which is nothing but 4. So by the end of this for loop, I have identified what is my minimum element in the array and what is the position of that element in the array. Okay. Post this, I'm checking if position is not equal to swap position, meaning because I don't want to swap the same element with itself, right? So in case 1 is in the first position, then all the other elements may not be less than 1, right? All the other elements will definitely not be less than 1. Therefore, your swap position and position will remain the same at the end of this for loop. Nothing would have changed. Min will still be 1 and position will also be 0. If that's the case, I don't want to swap 1 with 1 on the same position. Therefore, I keep a check if position is not equal to swap position, because in this case, now position is 20, position is pointing to 0, which is value 20, and swap position is pointing to 4 and the value is 1, and these are not equal. So I go ahead and perform the swap for 1 and 20. So 1 goes to the position of 20, which is the first element, and 20 goes to the last. Right? So this is how the array will look like: 1, 5, 100, 10, and 20 after the first pass is over. So up until this point, this is the first pass. After this, I call again selection sort recursively with the same array. Remember, this is an in-place sorting technique. What this means is we don't have any additional array or any other additional data structure in which we store the result. There's going to be a sorting on the same input array, therefore it's in-place sorting. We pass the same array and we just increment the position by 1, which means I now start looking at the array from position 5. This is the new array, 1, 5, 100, 10 and 20, and I start looking at the position 1, which is pointing to element 5, and I start comparing all the elements after 5, meaning after the first pass I know 100% sure that the element on the first position of the array is the correct position for that element. Therefore, when I take up the second element, I start comparing it with all the elements on the right side after that element. Same goes for the third element in the third pass, fourth element on the fourth pass, and after that you reach the last element, and this condition will kick in and it will say that you have reached the last element in the array, and therefore we just return the array and it should most likely be sorted. Okay, so that's the concept implementation for selection sort. And again, I have a print array method just to print out the elements of the array. Let me run this technique and let's see what is the outcome for this sorted array. Ideally this should be 1, 5, 10, 20 and 100. Now let's see what is the result. Keep in mind that when you have such algorithms, just a tip for you guys, always prepare a pseudocode, something like this. Dry run the pseudocode to understand the logic, so that when you do this kind of analysis, right, it will be very easy for you to write it or translate it into Java or any other programming language that you want to write this in, right? So generating a pseudocode is very important, and that will help you build your logic in the respective programming language that you use. So this particular Gradle project is building. Let's wait for it to execute. It should start execution now, and it's done. We see 1, 5, 10, 20 and 100, which is exactly what we expect out of this implementation. So that's it for this particular video. And for the time complexity, if you observe that we are taking each element and then we are comparing with the n-1 elements in the array, and then once we find the minimum value, then we do a swap, right? So for each element we look at the elements on the right, and for n elements it will also again look at n elements on the right, and by that logic we can say that the complexity of this sorting technique is also O of n square for very large inputs, because let's say there are 10,000 elements. I start picking up the first element, I'll have to find out the minimum and then swap it. Then I'll have to pick up the second one. Again, I have to compare against every single element on the remaining side of the array, and I have to again do the swap. So there's going to be one swap maximum per iteration, or there could be no swap because if the position and swap position are same, there will be no swap ideally. But the comparisons are going to be happening for every single element, because I need to find out the minimum element. So if you take that into position, we have a for loop and a recursion call here. So the complexity is going to be O of n square for selection sort. This time complexity is O of n square, but the space complexity is, I think, going to be still O of n, because we are going to use the same array. We are not introducing any new arrays, so the space complexity is still O of n, and that is because the length of the array could be n elements, right? So therefore the auxiliary space complexity is O of 1, and that added to the space complexity of n will get O of n plus O of n, which is basically O of n, right? So the space complexity is O of n and the time complexity is O of n square for this selection sort algorithm. If you like this video, hit the like button, subscribe to Code with Ani if you haven't already, share it with your friends, and I'll see you guys with another algorithm in the next one. Bye bye.